Chapter 16 is concerned with thermodynamics and in particular the topics of free energy and entropy. Our motivation in Chapter 16 is to try and gain an understanding of why some reactions are spontaneous and other reactions are non-spontaneous. So we're going to begin by defining those terms. So you've probably observed that some processes occur spontaneously. For example, if the temperature is greater than 0 degrees Celsius, an ice cube will melt. If a substance is combustible, say a fuel, and you set fire to it, it'll burn. If a substance is explosive and you give it a big shock or you detonate it in some way, it'll explode. Some things are very, very clearly spontaneous. And other things are very, very clearly non-spontaneous. For example, we never see objects rolling uphill. We'll never see ice cubes melting if the temperature, or we'll never see, water freezing if the temperature is greater than 0 degrees Celsius. And you've probably noticed this if you've ever had a flat tire, it will never, ever spontaneously inflate. So we kind of know it when we see it. If a process is spontaneous, what does that mean? Well, a spontaneous process in chemistry is one that continues without ongoing outside intervention. A non-spontaneous process from the chemist's perspective is a process that requires an ongoing input of energy in order to continue. So non-spontaneous doesn't mean impossible, it just means that you've got to keep feeding it energy in order for it to happen. An important quality of spontaneous and non-spontaneous processes is that if a process is spontaneous in one direction, it'll be non-spontaneous in the other. So for example, the fact that cars roll downhill means that cars don't spontaneously roll uphill. The observation that air spontaneously leaks out of a tire means that air does not spontaneously flow back into a leaking tire. As I mentioned previously, defining a process as being non-spontaneous doesn't mean that it's impossible for it to occur. For example, iron undergoes a reaction with oxygen to form rust spontaneously. That's why we have to paint bridges and things like that all the time. So iron will react with oxygen to form iron 3 oxide. This is a spontaneous process. That doesn't mean that the reverse process can't occur. In fact, we take very large amounts of iron 3 oxide and turn it into iron every year. We perform this reaction on the megaton scale. And this is this is a common industrial reaction to take iron 3 oxide and turn it into iron. However, because it is a non-spontaneous process, it requires a large input of energy, and we typically will perform this reaction at about 1800 degrees Celsius in what's called a blast furnace. And it's kind of an interesting reaction. We have a very hot furnace. And what we do is we drop in solid reactants into the top here. So in the top comes iron ore, coke, and limestone. And coke is just a source of carbon. Our iron ore is our source of Fe2O3. And because the temperature is very hot, the carbon gets converted into carbon monoxide, and that acts as the reducing agent for the Fe2O3. So it's kind of cool. The reaction actually occurs between the solid iron oxide and gaseous carbon monoxide as the iron 3 oxide falls through the furnace. So it happens from the top down, and it's a reaction between a solid and a gas that gives rise to the iron. Sometimes people mistakenly will assume that if a reaction is exothermic, then it is automatically spontaneous. And that is not the case. There are in fact many examples of endothermic reactions that are spontaneous. And a good example of this is the reaction between barium hydroxide and ammonium chloride. This reaction takes heat in, so it makes the surroundings cold, and it produces barium chloride solid, liquid water, an ammonia gas which has a characteristic smell. So I have a little video that's going to illustrate this reaction. Let's find it now. It's in here. Here it is. Okay. And
what I have is some barium hydroxide. Okay, I'm going to put this into the. In fact, you know what? I'm going to do this in one beaker. It's not that big. It's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully, we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk. Oh. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do is show how exothermic it is, how much heat this is taking in. So I'm going to make this wooden block wet. Okay. Now, you will see why I've done that in a second. So, I'm going to mix these two things together and carefully. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to make it. Okay, if you put that in coffee, oh, it's going to be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best way you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. That is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to. In fact, there's actually ice crystals forming on the side of there.
Can I touch the side?
Cool.
Cool.
Yeah. No.
So in that video, we see that reaction was clearly spontaneous, but it was very endothermic, and it got down to like about -10 degrees Celsius. So that's kind of cool. So similarly, though, there are many reactions that are spontaneous that are exothermic, and probably one of the most famous ones is the reaction that occurs in thermite, which is the reaction between iron 3 oxide and aluminum to make aluminum oxide and liquid iron, and this releases a lot of heat, and typically the temperature of this reaction will be around about 3000 degrees Celsius. It actually makes iron that is liquid iron. So what we learn from this is that the enthalpy change, the heat released or absorbed at constant pressure, is a really bad indicator of whether a process is spontaneous. We saw that some endothermic processes that take heat in, delta H positive processes, and also some exothermic processes that release heat, they can all be spontaneous. They can both be spontaneous. So enthalpy is not going to help us judge if a process is spontaneous or not. So the question we're left with is there a property of the system that allows us to predict if a chemical or physical process will be spontaneous? It seems that like energy and energy transfer is intimately related to spontaneity, but it's not clear at present, and we know that it is not the enthalpy alone. There's more to it than just thinking about the enthalpy change of the reaction. So let's consider a really simple spontaneous process. We're going to consider the gas leaking out of a hole in a tire. we're going to assume that the gas is made entirely of O2 molecules, and we know what the Lewis diagram for O2 looks like. And we're going to assume that the temperature remains constant. That is, that the gas particles do not undergo a change in their energy. And we're going to think about how the energy of the gas particles, of our O2 molecules, is distributed, and how that distribution of energy changes from being inside the tire to being outside the tire. So the energy of this gas is distributed amongst three fundamental types of movement. There's what we call translation, where the molecules move from one place to another. There's what we call rotation, where the molecules spin about their center of mass. And then there's what we call vibration, where the molecules kind of stretch and contract against that bond. Now, at a given temperature, there will be a fixed total amount of energy, but the way that it's spread amongst these three different things might change. So at one point in time, you might have lots of translation occurring and not much rotation occurring, and then a moment later, you might have a lot more rotation occurring and only a little bit of translation occurring because the molecules have collided with one another, and that kind of set them spinning. So the important thing to recognize for this particular system is, because it's at a fixed temperature, the total energy remains constant, but there's going to be many ways that it can distribute that energy amongst the different types of motion, and it's going to change with time. Sometimes it's spinning a lot, sometimes it's vibrating a lot, sometimes it's translating a lot. You know, it's just going to change with time as the molecules bounce off one another. At a given temperature, there'll only be certain vibrations and rotations that are available. So as you go to kind of higher and higher energy, there's, you know, a greater variety of ways in which molecules can spin and stretch that are possible. But as we at a lower energy, say we're down here, then you might only have like one or two ways that the molecule can rotate and vibrate. But the important thing for us is, because the temperature of our gas doesn't change, the number of ways that it can rotate and vibrate that are possible for the gas to rotate and vibrate doesn't change. So what does change? Does the speed change? Well, at a given temperature, the energy of our gas is fixed, so we will have a fixed distribution of speeds. So we know that for a gas, at a given temperature, there will be some particles that are moving very quick, some that are moving slow. Most of them will be moving at a speed near the root mean squared speed. And, you know, the only thing that changes this distribution of speeds is moving to a different temperature. But in our case, the temperature is fixed, so the distribution of speeds doesn't change with time. The possible speeds is not a variable here because the temperature is fixed. So what does change? We've talked about how fast they're moving, we've talked about how they're rotating and vibrating. What is different about the gas when it is outside the tire? Well, when we increase the volume of our sample of gas from being inside the tire to being just in the atmosphere, what we have increased is the number of ways that it can move, the number of ways that the gas particles can distribute their translational energy. So when our gas molecules are contained within the tire, it's kind of like a squash ball being contained within a squash court. There are only very few, there's a minimal ways in which those gas molecules can move. They are confined within a particular region of space. But once the gas molecules leak out of the tire, they can be anywhere in the atmosphere. They have much greater freedom with respect to how they use their translational energy. So that's what's increased, right? The number of ways the molecule can translate. That has increased enormously for the gas molecules when they leak out of the tire. So what we're going to do is we're going to define this thing called a microstate. And what a microstate is a unique distribution of particles amongst what we call their accessible energy levels. it's a kind of like just how is the it's a way that a set of particles can use their energy, right? It's just an accessible means that the particles can it's just a manner in which the particles can distribute their energy amongst the available rotations, translations, and vibrations. The effect of the air leaking out of the tire is that we've increased this number of ways that the gas can distribute its total energy. When it's contained in the smaller volume within the tire, because the number of translations that are possible is reduced, we have a fewer number of these microstates. Now, when we're in the higher volume, where the gas is has the entire atmosphere that it can move in, then we have a larger number of states that are accessible. So what's really happened is that the energy of the gas outside the tire is what we call spread out more across more microstates. There are just more ways of the gas particles to spend their energy. Okay, so this is kind of an abstract concept. You should have an attempt at these first 3 problems here, and we'll be going through that in the Zoom session on Wednesday.